So we're going to discuss some fundamental concepts in fluid mechanics. Some elements you might have met before. Cover basically the integral and differential form of fluid mechanics and some concepts related to frames of reference and thermodynamics. All these concepts are quite important for looking at compressible fluid mechanics, and the continuing description is also used when we look at CFD formulation. Classical thermodynamics is built around a series of laws, and the first one is a conservation principle. That is the sum of the internal energy determined by the heat that comes into the system minus the work that's done. So the notation being that if we have a closed box, the heat comes in and the work is the action work W is what's. We're going to use this when we look at heated pipes and reactions and version of energy to mechanical work. Second law of thermodynamics is to do with the relationship between entropy and the heat that comes into the system. The main thing is that entropy is dq dt, it's dq over t, and I'm probably using this in the compressible fluid mechanics is a discriminator between different sets of solutions, and the discriminator basically is expressed in terms of inequality. That the only conservation principle where it is expressed in terms of an inequality is that the entropy cannot decrease. But mainly we use this as a discriminator, as we see later on. The equation of state is pretty critical. It expresses the relationship between P, rho and T. Quite a difference between the type of equation of state that you have for a gas and a liquid. We do more of the equation of states for liquids in year 4. We're going to be using the ideal gas equation in most of the analysis, and that basically is a relationship between pressure, density and temperature, P equals rho RT. R being the gas constant for the gas that we're using, and usually, not usually, it's defined in terms of the ideal gas coefficient divided by the molecular mass of the gas. Critical thing that we use here is concept of enthalpy and the internal energy. So for an ideal gas, both are proportional. So for the general case, dH is proportional to Cp dt, and for ideal gas equation or ideal gas model, Cp and Cv are constant independent of temperature. When we look at hypersonic flows, which we'll cover just briefly at the end of the compressible fluid mechanics course, we'll be looking at how this relationship is modified when we have Cp, specifically Cp as a function of T. When we look at things like CFD formulations, this relationship is quite critical for putting in kind of real gas equations. So gamma is the isotopic index for a diatomic atom like oxygen or hydrogen or nitrogen. Then it takes a value of 1.4. And since air is mostly composed of nitrogen and oxygen, this is why we're going to take this as a kind of overriding assumption in most of the analysis, apart from those cases where we do some examples with CO2. So this notation is pretty crucial. It kind of sets the scene for lots of the analysis. But so we use so the term adiabatic is basically a system in which there's no heat comes in and no work is done. And this is a kind of scenario where we may have very strong changes within the flow itself, accompanied by a strong shock. Isentropic is, and so adiabatic tends not to be, well, it's not reversible. Isentropic is a case when the entropy is constant, there's no change in entropy, and this corresponds to weak changes. And so we use these terms all the way through the course, and so it'll be pretty clear. So there are cases that are, I mean, shocks are not isentropic, but expansion waves are. And when we're putting in heating gas in pipes or having a chemical reaction, then of course it's not adiabatic. And so we need to then look at how our internal energy changes in relation to the chemistry that's being that's occurring. Now, conservation principles basically they're based around analysing parcels of fluid, and the kind of starting point of this is whether those parcels of fluid are moving or stationary. And so in the whole of the physical sciences, not just fluid mechanics, we have two frames of reference. One is a kind of what is called an Eulerian frame of reference, which is essentially fixed frame, and you might think of making measurements of the flow at a fixed point, and that would be an Eulerian measurement. An Eulerian framework is the idea that we know all the information at fixed points, and that would be sort of reflecting a kind of computational study of something where the mesh isn't moving. An alternative but equivalent frame of reference is something that moves with the fluid itself. So here we were thinking of parcels, tracking the parcels with time. They're equivalent, but they're quite difficult to map one on the other. And it's often said that in order to understand in a reasonably complete fashion physical processes, you need a combination of both. And so we do quite a lot of work on applying a Lagrangian framework to understand some complex flow processes. Both had advantages and disadvantages. So depending on which frame of reference you use, your conservation condition will be, law might be simple or might be difficult. That's for the integral form. Conservation conditions, as we've probably reiterated quite a few times, you can either think of the equation, think of the physics, or think of a word equation. So they're all pretty equivalent. The idea of conservation mass is simply what goes in goes out. And so if we have a parcel of fluid that is moving around in time, u being the speed of fluid, if this is a really tiny volume, essentially what you're saying is that if that moves with the flow, we're saying the mass in that control volume that's also moving with the flow is not really changing. So integral of rho dV over a volume, and the volume being Lagrangian, is unchanged in time. You can convert that to a differential form, so you can convert that to by looking at in more detail about how that volume might move into form. And the differential form of conservation mass is that the density changes in this volume because of it's being squashed by the flow itself. So if there's a div u here, this tells you whether the flow is being squashed or expanded. The capital D here tells us that change is following the fluid element itself. And so we will make use of this form. A compressible flow is one in which this doesn't equal 0. In other words, div u is not equal 0. Now, doesn't mean that it's everywhere. So you've got a flow through a flame. For instance, div u is going to be 0 on the left hand side, div u is going to be 0 on the right hand side, but it's not going to be 0, it's going to have a very large change where that reaction is occurring. We don't deal with incompressible fluids. Maybe we do one tutorial question as a comparison for pressure drops in pipes. But for incompressible fluid, which you've done year 1, 2, div u equals 0. Conservation of linear momentum, remember there's linear and angular, is essentially the force on your control volume depends on the action of the stresses and the body forces acting on it. So that will be the integral. This is expressed in terms of Lagrangian volume and surface. Sigma, bold sigma, is a stress tensor. It's a tensor, so it's a 3x3 kind of matrix. Is pressure, tau is viscous stresses. In the compressible fluid mechanics course, we take an inviscid approach. We neglect viscous effects in our discussion. And so when we're talking about neglecting viscous effects, what we're really saying is that the viscous stress tensor is not important. That's the integral form. The differential form basically becomes the rate of change acceleration with the Lagrangian derivative or convective derivative, however you describe it, is div sigma plus the body force. And of course, for something with no gravity and no viscous effects, then we end up with Euler's equation. And this isn't saying rho is constant. Rho can be a function of position and time. It's just implicitly understood to be the case. So conservation of angular momentum tells us something quite special about the stress tensor. And again, the same thing is that the angular momentum of your fluid element, angular momentum is obviously x cross the velocity. The momentum bit, x cross u times rho, gives us the angular momentum per unit mass integrated over the volume. Is determined by the moment of the forces on the surface and the moment of the body force acting. And this reduces down to a simple, quite important critical relationship, is that the stress tensor must be symmetric, providing there are no the conservation of energy simply says that the sum of the internal energy plus KE, internal, plus kinetic energy, Q being the speed, determined by the action, or determined by the work done by the viscous stresses on the surface. The diffusive flux through the boundary, and the work done by the body force. So the differential form essentially has got these two additional terms, diffusion of heat and work done by the body force. So if they go and we take an inviscid approach, then this becomes div UP. And you can kind of see if we look at changes as we add vectoring through structures, then we essentially reduce the equation of motion, the conservation condition in differential form, back to basically E plus a half Q squared plus P over rho is constant. So we kind of reduce ourselves to conservation condition for ideal gas. So the differential form of the energy equation can be simply written in this particular form, and we can integrate this along a streamline and determine how the relationship between pressure and velocity is expressed. energy is ultimately all communicated into viscous dissipation. So even if it's a turbulent flow, there's a cascade down to viscous scales. And this is the kind of activity that Joule originally did when he was looking at the conversion of mechanical work to production of heat. So his apparatus was fantastically simple. It's basically a bucket with a paddle in it, and the longer he churned, the hotter the water became. And that's in the Science Museum. So the relationship between pressure and speed depends on the configuration you're looking at. So what is familiar to most students from their year 1 is the case of isothermal flow, where there is when there's no vorticity. Along the streamlines, the relationship between pressure and velocity. So for potential flow problems and flows that are inertially dominated, then P over rho plus half Q squared is constant, and that's determined by either you could determine it by the momentum equation, or you can do it through consideration of mechanical energy. And the energy thing is quite important because we'll use a specific formula when we look at compressible flows. When it's unsteady, of course, we introduce this additional contribution from the flow acceleration, where u equals grad phi, and phi being the velocity potential. Now for adiabatic flows, so we're going to use these quite a lot, then we've got the sum of the internal energy plus kinetic energy plus the pressure work potential, P over rho, is a conserved quantity. And if it's an ideal gas, then we can express E in terms of CVT, and P over rho is RT, and then combined together we find a relationship between P over rho and Q squared. And this is used pretty much all the way through our analysis of compressible fluid mechanics. This is written in a dimensional form, but when we come to look at or analyse this, we'll work in terms of Mach number. When we come to analyse compressible flow problems, we usually do this in relation to a reference state. The reference state might be one that might be realised, or it might be one that's just conceptually quite useful in order to solve problems or understand problems. So there are two reference states which are used in compressible fluid mechanics. One is what we call stagnation flow condition. This is a condition under which we assume that the flow is at rest. However, it's brought to rest. This isn't a condition that can necessarily be realised or isn't realised. And we'll show its utility when we look at conservation of energy. So if we take our conservation of energy equation and we determine what the speed of sound is, the speed of sound being dp d rho at constant entropy, we find that's equal to gamma RT or gamma P over rho. So what we're going to manipulate this and express in terms of Mach number. So first thing is a CP is this, and the second thing is that the Mach number we make use of is the Mach number is U over C. So put those things together, our conservation of energy is a conservation condition. Adiabatic and ideal gas, it becomes this. And this is quite interesting. So it becomes this T plus times 1 plus half gamma minus 1 m squared is a constant. And we can set that constant to be something arbitrary, a reference state. And so one thing we might want to do is perhaps choose it has dimensions of temperature first of all, and we can choose a value, let's call this a T reference. it's a constant. We can determine what it is if we know the state. And one very useful value is to take a value where the Mach number is 0, and we call that our stagnation temperature, T0. Now, having a Mach number 0 means the flow is at rest, but actually if we introduce something to bring the flow at rest, we perturb it, we introduce shocks, most certainly. And so the stagnation temperature in this particular case is a kind of hypothetical temperature, but it has a lot of utility because it's conserved. So if we take our conservation condition, T1 plus half gamma minus 1 squared, is a constant, is T ref, we said it'd be T0, T0 being our stagnation temperature, then our conservation condition becomes something very, very simple. So regardless of whether the flow goes through a shock or not, T0 is a constant. And so in this particular case, in a flow that's under adiabatic conditions, so can be strong and non-linear, T0 is a very useful concept, and so I always advise students to kind of remember this equation. Now if we look if we do the same thing and say, well, this is obviously a constant over temperature, well, we can write this as P, we can write this as P rho times a constant. Now what we could do is say, look, we don't know what that constant is, but let's call it P naught over rho naught, to call the whole thing a constant. And what we know from this is, since it's conserved quantity, that ratio P naught over rho naught is a conserved quantity through a shock. Individually, though, P naught and rho naught are not conserved for adiabatic flow conditions. But if you relax that constraint that it's adiabatic and assume it's isentropic, then we end up with another relationship between P and Mach number. And this becomes very useful when we look at something like an expansion fan, where the flow is isentropic. So, under adiabatic conditions, stagnation temperature is a useful concept, a useful quantity. It's used a lot in our analysis. P naught over rho naught is a conserved quantity, but P naught and rho naught individually themselves are not. If you then assume the flow is isentropic, then we can find a relationship between P and Mach number. And in this case, we do have this stagnation pressure and stagnation density. Stagnation pressure is used a lot to assess the potential for a gas turbine engine to do work. You don't want losses and to reduce that. So that becomes a very useful measure of the efficiency of your engine. Now that's one reference state, a stagnation flow reference state. The other one is a sonic flow condition. And this is where the Mach number is 1. So flow in a pipe, you would not want the Mach number, you wouldn't want the flow to be 0 anywhere, where there is a potential of there being a stagnation point somewhere in flow past a bluff body. So we use stagnation temperatures for general compressible flows, and we use sonic flow reference state. The Mach number is 1 generally for flow in pipes. And that concludes our discussion of reference states. Just one thing to note, for a critical reference state, it's called critical reference state, we use a star. Thank you very much. Bye bye.